Welcome to our segment on distant stars. By distant stars, I mean those stars that are so far away that parallax doesn't work anymore. Stars like this one, V838 Monocerotis. In order to know how far away V838 Monocerotis is, we'll need a new way to determine distance. To do that, we're going to build out a diagram that maps the star's color to its luminosity. Then we're going to study the nature of light that comes from the stars. And with that knowledge, we'll be able to use that diagram to determine the intrinsic luminosity of stars like this one. And with that, we'll know how far away they are. So let's begin with our study of light. We know a few things about light. We know that light is electromagnetic radiation created by moving electrons. With help from Jupiter's moon Io, as we discussed in our segment on the solar system, light travels at 300,000 kilometers per second, or 186,000 miles per second. And as we have seen, stars vary in apparent brightness, and knowing the star's distance, we can use the inverse square law to find its intrinsic luminosity. The other thing we know is that stars have different colors. And very interestingly, color tells us a lot more than you might think. But to understand color, we need to know more about light. Light, as we currently understand it, has a dual nature. We can view it as a particle, like a photon, or we can view it as a wave that can interfere with itself. Although we haven't been able to reconcile these two incompatible views with one underlying understanding, what we do know has turned out to be surprisingly sufficient for the distance ladder. For color, we view light as a wave. Here's a simple wave. It has a repeating cycle, a wavelength, and a frequency in cycles per second. Newton showed that the sun's light can be dispersed into the colors of the rainbow with a crystal. This effect comes from the wave nature of light. Different colors represent different light frequencies. The higher the frequency, or inversely, the shorter the wavelength, the more it's bent by the crystal. This produces a spectrum of light with blue and violet at the high frequency end and red at the low frequency end. An important relationship between energy and light is that a light's energy is directly proportional to the frequency. So when physicists see color, they think energy. Red is low energy light, and blue is high energy light. Here we see the full electromagnetic spectrum with visible light in the middle. Radiation with longer wavelengths and smaller frequencies than red light is called infrared, and still longer wavelengths are called radio waves. Moving up the energy scale, radiation with shorter wavelengths than violet light is called ultraviolet. Still shorter wavelengths are called X-rays, and the maximum energy radiation is called gamma rays. Celestial objects shine in radio to infrared, visible light, and ultraviolet to X-rays. One of the very important relationships between light and matter is called blackbody radiation. Turns out that the color of most matter at high temperatures depends completely and totally on the temperature. Nothing else really matters. Take a look at this iron rod as it heats up. See how it goes from red hot at the outer edges through yellow to white hot at the center? If we could get it hot enough, you'd see it turning blue. Here's why. As temperature increases and the electrons start moving more rapidly, two things happen. 1. The object emits more radiation at all wavelengths. and 2, the peak emission frequency shifts towards the shorter, higher energy blue wavelengths. As the heating starts, the radiation is all in the infrared range, so we can't see it. As the temperature approaches 2000 degrees Celsius, we begin to see red. We've seen the red star Aldebaran. It's a good example of this. By 3000 degrees, the red has morphed to orange. Arcturus is an example of this. By 4000 degrees, it is quite yellow. Capella and our own Sun are yellow. Around 6000 degrees, it is turning white. The star Sirius A is an example of this. And by 10,000 degrees, it has a distinct bluish color. Spica is a good example of a blue star. So the bottom line is, measure the color of a star by the frequency of the light it emits, and you've determined its temperature. It's that simple. Now that we know star temperatures via their color and luminosity via their parallax distance, we can build a diagram I mentioned in the introduction. In 1913, Ingvar Hertzsprung and Henry Russell began mapping these star temperatures against their luminosity. Note that the horizontal axis is mapping temperatures in the decreasing direction. If we begin with the stars we use to illustrate blackbody radiation, Aldebaran, Arcturus, Capella, our own Sun, Sirius A, and Spica, and throw in a few others like Sirius B, Wolf 359, Polaris, and Vega, we get a graph that looks like this. With this small sample, it looks like any combination of temperature and luminosity is possible. But Hertzsprung and Russell meticulously plotted all the stars with known distance and luminosities, and they got this. Here we see that most stars fall on the diagonal line, from the upper left hot blue luminous stars down to the lower right, cooler, dimmer red stars. But there is also a grouping of stars well below the main line, and 2 groupings of stars well above the main line. This is the Hertzsprung-Russell diagram, or HR diagram for short. It is one of the most important tools in understanding stars ever devised. It tells us a great deal about the life, death, and age of stars. And, more importantly, for our purposes, it can tell us how far away stars are. But in order for the HR diagram to do this, we need to know more about what makes stars shine, and we need to know more about the full spectrum of light we receive from these stars. In our segment on Starbirth Nebula, we'll cover how stars form from giant hydrogen clouds collapsing under the force of gravity. They start shining once the pressure and temperature at the core reaches the level needed to support hydrogen fusion. The fusion of hydrogen into helium converts some of the mass into energy. And because E equals mc squared, and c is a very big number, the process generates a great deal of energy. The more hydrogen there is in the collapsing cloud, the more massive the star. The more massive the star, the more intense the pressure in its core. The more intense the pressure, the higher the temperature. The higher the temperature, the greater the star's luminosity. Thus, the diagonal line on the HR diagram represents the main sequence for stars burning hydrogen. The upper left blue and white hot stars are high-mass stars, many times more massive than the Sun. The middle region, yellow and orange stars, are closer to the mass of the Sun. The lower right stars are cool, low-mass stars that are a fraction of the mass of the Sun. When a star runs out of hydrogen fuel, the core contracts and gets hotter. This heat expands the outer layers, reducing the density and turning the star red. The star moves off the main sequence and enters the realm of giants or supergiants, depending on their original mass. When a red giant, with the mass less than 5 times the mass of the Sun, runs out of fuel, it explodes and leaves behind a dim, hot, tiny star called a white dwarf. We'll discuss these processes more in our segment on planetary nebula. We'll cover the endgame for more massive stars in our segment on supernova. Now that we understand the meaning of the HR diagram, let's see how we can use it to find out how far away a star is. For that, we need to view light as a particle and examine its spectrum. Early in the 19th century, German chemist Joseph Fraunhofer invented the spectroscope, an instrument to automatically separate light and mark the wavelengths. In so doing, he discovered that when he spread sunlight into a spectrum, the spectrum was crossed by a great number of fine, dark lines. He had no idea what these dark lines were, but today we know that they were the key to learning what stars are made of. Remember the red and green light of the aurora borealis and the structure of molecules we discussed in our segment on the heliosphere? The aurora is a good example of light being emitted as electrons change energy levels. But for our purposes here, we want to examine what happens when light from the center of a star passes through the gases in the outer layers on its way to us. Here's how it works. When a photon with exactly the right energy level hits an electron orbiting a nucleus, its entire energy is transformed to the electron, which jumps to a higher energy level with a larger quantum number. The photon is eliminated. This creates absorption lines in a star's spectrum as light from the star travels through the star's atmosphere. Every atom and molecule has its own spectral line signature. So by observing the absorption lines in a star's spectrum, we can tell what elements are present. When scientists discovered connections between groups of spectral lines and star temperatures, they developed a set of spectral classifications to highlight this connection. Every star we have seen so far fits into one of these classifications. Our Sun is spectral class G and has around 67 elements in its photosphere. Here are a few identified by their spectral signature. Turns out that hydrogen is 50 to 80% of most stars, and combined with helium, they make up 96 to 99% of all stars. Star spectra has one more characteristic called luminosity class that enable us to determine whether a star is on the main sequence or not. This is the key to using the HR diagram to determine a star's distance. If you recall, the evolution of a star off the main sequence involves the expansion of the outer layer to gargantuan proportions. This makes the density of the gas in the outer layer of a giant much less than the density in the outer layer of a star on the main sequence. It turns out that the photon absorption characteristics of closely packed atoms makes the spectral lines fuzzier. For a given spectral classification, the fuzzier the spectral line, the smaller the star. Roman numerals are used to identify luminosity classes. Our Sun is class 5, a main sequence star. We'll use Betelgeuse to illustrate how star spectra works with the HR diagram to determine a star's distance. First, we use the star's color, temperature, and spectra to find its point on the horizontal axis. Looking up the vertical luminosity axis, we see Betelgeuse could either be a main sequence star or a giant. Examining the luminosity class, we see that it is very sharp, implying that Betelgeuse is a supergiant. Now, drawing the line to the vertical axis, we see that the star's intrinsic luminosity is 120,000 times greater than our Sun's luminosity. Measuring the apparent luminosity and using the inverse square law, we get the distance. If stars everywhere behave like the stars in our neighborhood, then the HR diagram can show us how far away they are. Astronomers call this technique spectroscopic parallax, but we'll just stick with HR diagram. Now let's take a look at some distant stars. This star, known as V1331 CYG, is a young star that is starting to contract to become a main sequence star similar to the Sun. It lies inside a dust cloud. We're looking down on the star at one of its poles, which allows us to see the dust cloud enveloped around it. Usually, for young stars like this, all we get to see is the dust cloud. The star at the center of this picture is a red supergiant called UY Scuti. It is very dim, but appearances can be deceptive in astronomy. This star is actually about 340,000 times more luminous than the Sun. In fact, it's a candidate for being the largest star in the entire Milky Way galaxy. Astronomers believe the actual size of UY Scuti is big enough to hold 5 billion suns. Here we see the superhot star WR124 and the hot clumps of gas it is ejecting into the space around it. Ejection gases are traveling at over 150,000 kilometers per hour. That's 93,000 miles per hour. The cloud, known as nebula M167, is estimated to be no more than 10,000 years old. That's very young in astronomical terms. Here's a Hubble image of the luminous blue variable star AG Carina. It has evolved from the main sequence with 20 times the mass of the Sun. AG Carina is losing its mass at a phenomenal rate. Its mass-to-energy conversion is creating powerful stellar winds with speeds up to 7 million kilometers per hour, or 4.3 million miles per hour. These powerful winds are responsible for the shroud of material visible in this image. You'll recall how we used the inverse square law when we covered star luminosity in the nearby star segment. We measured the brightness and calculated the distance from parallax measurements to get the luminosity. But if we had a way to know what the intrinsic luminosity of a star was, we could use that, along with the apparent brightness, to get the distance. For example, if we measured the brightness of a 10-watt candle from some distance away to be 1/10 of a watt per square meter, we could calculate that the candle is just under 3 meters away. A celestial object with a known luminosity is called a standard candle. But until 1912, there were no known standard candle stars. That changed when Henrietta Leavitt published her findings on Cepheid variable stars. Like Polaris, Delta Cepheid is a binary star system and a Cepheid variable star. Cepheid stars undergo periodic changes in luminosity. Delta Cepheid is among the closest stars of this type of variable, with only Polaris being closer. Most stars have some variability in their luminosity. Even our Sun varies on an 11-year cycle of sunspots, but delta Cepheus variability is caused by regular pulsation in the outer layer of the star. Here's its light curve, showing luminosity changes over time. The pattern is quite regular. Early in the 1900s, Henrietta Leavitt thought to plot Cepheid luminosity cycle periods against luminosity. She found that the period of these stars varied in proportion to their absolute brightness. This was very interesting, because as we have discussed, once we know the intrinsic luminosity of a star, we can easily calculate its distance. Leavitt's discovery made Cepheus stars true standard candles and changed the history of astronomy. RR Lyra is a variable star, like Delta Cephei. As the brightest star in its class, it became the namesake for the RR Lyra variable class of stars. The relationship between pulsation period and absolute magnitude of the RR Lyras make them good standard candles. They are not as bright as Cepheid variables, but there are a lot more of them. They are extensively used in globular cluster studies, including the studies that helped us understand the form and size of our Milky Way galaxy. Zeta Geminorum is an intermediate luminous supergiant. It is also a classical Cepheid variable. HIP 13044 came from outside our galaxy. It was part of a former dwarf galaxy that merged with the Milky Way between 6 and 9 billion years ago. Chi Lyrae is a carbon star. It has used up most of its hydrogen fuel and is now fusing helium into carbon. Here we see the Summer Triangle, a giant triangle in the sky composed of 3 bright stars, Vega, Altair, and Deneb. Deneb is a blue-white supergiant. It's one of the biggest white stars known, at 203 times the size of the Sun and around 19 times more massive. Deneb's solar wind is blowing away material at a rate that results in its losing mass 100,000 times faster than our Sun. This star is very faint. It is made of almost purely hydrogen and helium, with only extremely small amounts of heavier elements. We estimate that the star is probably more than 13 billion years old. That would make it one of the oldest stars in the universe. Mu Cephei is a red supergiant star. In fact, it is one of the largest and most luminous stars known in the Milky Way. This star could fit 1 billion suns into its volume. Eta Carina, 10,000 light-years away, is estimated to be 100 times more massive than our Sun. It is one of the most massive stars in the galaxy. It radiates about 5 million times more power than our Sun, and its mass, as you can see, also makes it very unstable. Hubble's latest image of the star V838 Monocerotis reveals dramatic changes in the illumination of surrounding dusty cloud structures. The effect, called a light echo, has been unveiling never-before-seen dust patterns ever since the star suddenly brightened for several weeks in early 2002. During the outburst, the normal faint star suddenly brightened, becoming 600,000 times more luminous than our Sun. Hubble has captured this image of a hypervelocity star over 250,000 light-years away. It's 200,000 light-years above the galactic plane and traveling at 722 kilometers per second. That's 450 miles per second. That's fast enough to escape the galaxy's gravitational grip. Astronomers think it was a member of a multi-star system and was jettisoned by the black hole in our galaxy's central bulge. We'll cover black holes when we get to the segment on the Milky Way. The black hole's tremendous gravitational pull stripped one member while violently ejecting the other member deep into space at these high velocities, conserving the system's momentum. The first example of hypervelocity star was discovered in 1995. This one, US 708, is the second such star to be discovered. It is an extremely rich helium hot white dwarf, moving at 1,200 kilometers per second. That's 746 miles per second. That makes it the fastest star ever discovered. It crossed the galactic plane around 14 million years ago and is thought to be the companion of an exploding star that sent it out into intergalactic space. In our segment on nearby stars, we reached as far as parallax can take us by using the space-based satellites Hipparchus and Gaia. But if that's all we had, we'd know very little about our galaxy and almost nothing about the universe beyond. But in this segment on distant stars, we introduced two new rungs for our cosmic distance ladder. One is the Hertzsprung-Russell diagram for estimating a star's luminosity and therefore its distance. The other is variable stars that work as standard candles, stars that tell us their intrinsic luminosity by the period of their variable luminosity cycles. In particular, we covered Cepheid and RR Lyra variables. These rungs in our distance ladder have taken us across the entire Milky Way. In subsequent sections, we'll use these distance ladder techniques on star clusters, star-birth nebula, star-death nebula, also known as planetary nebula, our next segment.